welcome to Module 16 on regularization, specifically L2 and L1 especially. So this module falls within the 5th cluster on regularization and optimization basics in general. Specifically, this is the bridge sort of between the evaluation and bias variance, topics of recent modules where we talked about how we know a module is actually good, and then optimization, which we've kind of touched on to large extents already, but just going a bit deeper about how we actually fit models theoretically. So this is, regularization is an important part, which is both theoretical and practical. We're going to focus on intentionally controlling model capacity to improve generalization here. That's kind of the underlying aspect of this form of regularization. At the end of this module, you should be able to explain what regularization is and how it relates to model capacity, and even explain what model capacity is. You'll be able to write down and interpret regularized objectives with L2 and L1 and elastic net penalties. You'll be able to implement and compare L2 and L1 regularized models in Python on small data sets, or maybe even large data sets. You'll be able to analyze how regularization strength affects training versus validation performance and learning curves, and then justify your choice of regularization. A lot of these terms we haven't defined yet, but this is all what you'll have learned by the end of this module. So we'd like to understand when a good training loss can actually end up resulting in bad consequences. So imagine you have a complex model, and then the training error you get through the process of training goes down to almost zero. But then you have some validation data, and accuracy drops, or the loss explodes, or the predictions are just unstable across cross-validation or across other forms of splitting or sampling. So what we want is models that generalize and not just memorize. So performing very well on a training set of data might be a symptom of memorization on that data, and the failing to generalize certainly is related to that. Also, we want to make sure that just the training loss by itself and optimizing just the training loss does not penalize flexibility, right? So there's a kind of a tension between being very good on the training data and being flexible to other samples of data. We want this tension or this trade-off to be somewhat in balance. Just to make that clear what I said, didn't say imbalance, I said in space balance. So regularization, the topic of today's module, is essentially, it's a broad collection of methods, some of which we'll introduce today, some of which will be in different modules in the future. But this is, in some sense, a discipline for models. It will explicitly discourage very complicated solutions. It'll explicitly discourage overfitting, and it'll do this typically by trading off a little bit of bias for reduced variance. And you can revisit Module 14 for definitions of bias and variance. So let's scaffold our concepts. The idea of capacity I'm going to use very loosely here. I'm not going to define it very mathematically, but it can mean multiple different things, like specifically in terms of implementation. But generally, high level, it refers informally to how flexible a model is. So high capacity could be a model that's a deep neural network with 100 billion parameters. Similarly, it could be a high degree polynomial, and a high degree polynomial might only have on the order of a dozen, maybe 24 coefficients or weights to adjust. So it depends on the context, it depends on the architecture, what I mean by high capacity. But what's common in these two approaches, the deep neural networks with 100 billion parameters and the high degree polynomial with just 12, both of them are high capacity in the sense that they have, relative to the task, a good amount of flexibility in terms of what it can represent by tweaking the available parameters. So to a large extent, capacity just means the space of weights or adjustable parameters, and how large it is compared to whatever the signal is in the data set that we have at our disposal. The contrast is low capacity, so a simple linear model with just like a few features would be an example of something that might underfit. It might not really be a good representation for whatever the complexity level is of the signal in the data we're dealing with. So this is an informal way of talking about capacity, but you can think of the informal term of capacity as just how much space is in the model to encapsulate or represent the meaning of the data. So again, just to note here, like what constitutes high capacity or low capacity, there's no one threshold for that distinction. It is based on context. Sometimes a few dozen parameters, sorry, spelling mistake, parameters can be considered too much. Sometimes 70 billion parameters are too few. It's a function of the architecture, it's a function of the data set, it's a function of the task you're dealing with, it's a function of many contextual aspects. So here's the high-level concept of regularization. All regularization really is an explicit preference for simple parameter settings in the training objective. So before, our training objective was to minimize the empirical risk, be it the mean squared error loss or the like classification error, or even something generative like cross entropy or likelihood that we saw recently in maximum likelihood estimation. We want that's one aspect of the preference, but we also want the parameter settings to be simple, which is a second aspect of our preference for an overall training objective. So this doesn't mean that we'll necessarily have fewer parameters, although spoiler alert, it can mean that. It just basically means that the parameters we have, we want them to fluctuate less and to be more or less contained, to be calmer, to speak informally. Somewhat less informally, or more formally, we're going from the left to the right here. So instead of just minimizing a loss between a target y, the truth, and the prediction f of a given input, f of x, instead of minimizing this average loss, we want to minimize that plus some extra term, lambda times omega of w. We're doing a couple of things here. So we're introducing we're changing the parameterization from theta to w. I think I might have mentioned in this in class where we're going to be mostly following the trends or the standards within the machine learning subarea. This isn't like a fixed rule or anything, but sometimes the more theoretical aspects of machine learning uses theta to represent the parameters. When we get into a bit more engineering, we tend to see W come up a lot more. W being the weights, meaning the parameters. So theta and W are totally interchangeable here. So when you see W here, you can think of theta in our old conception. And we also have this function omega. Omega right now is just a penalty on the parameters. We're going to define it in a second, but it just basically is kind of like a loss. It's a bad thing. We want to minimize it. We don't like this penalty omega. And then lambda, this is another hyperparameter. It's greater than or equal to 0. If it's 0, then we just get the regular loss function. If it's bigger than 0, then we have some weighting applied to the penalty, the omega penalty, and this basically controls how much we care about regularization. So lambda is something we can tune by hand, and again, back to a class we had recently, there's ways to tune hyperparameters like this, ones that we can tune by hand, by using data and the validation set. We'll talk about that a bit later as well in another module. Here's the idea of capacity versus the data. Here we have the expected generalization error, which is this blue curve. Errors on the y-axis. Model capacity or complexity is sort of normalized as just for conception here on the x-axis, from like minimally complex to very complex. And then we have the training error. The idea here is that as you get a more and more complicated model, you expect the training error to go down as the complexity goes up. Like the more complicated model can have more capacity to tune itself onto the specifics of the training data set, to overfit to it essentially. So training data generally is going to go down as complexity increases. This is in contrast with the generalization error. So how much error do you expect to see when you go from a training data set to another data set you haven't seen before? And this is represented as this blue curve. Like things generally get better as you increase a model from like absolute no complexity or capacity to something a bit better, but then at some point you start overfitting and then generalization error goes up. The sweet spot, again, we care mostly about generalization. Training data is obviously important, but the name of the game, so to speak, is generalization. We want to deploy these models eventually outside of the lab, so we want to make sure that our expected generalization error is as low as possible, so our sweet spot is just obviously the low end of this curve. And the idea, of course, is that if we increase lambda, so if we have stronger regularization, we can kind of bring down the capacity to some extent. And we'll see that in a second. So the generalization error is U-shaped. The left side is bias, high bias, that's underfitting. The right side is high variance, that's overfitting. And then the middle is sort of the sweet spot. And yeah, indeed, for a fixed model family, so a particular architecture, even a neural network, if you increase lambda or you decrease the capacity, this reduces the effective capacity, but it can result in better generalization. So what's an anti-example? What's something to avoid or some kind of mental problem to avoid? First of all, thinking of regularization as if it's magic. Occasionally, when people get a little bit more familiar with machine learning, they get to a point where they just, like the only tool they have at their disposal is using more regularization. So they encounter a problem, things don't generalize well, they're just going to regularize. So imagine you have a ton of label noise, or you have some leakage or some other problem that exists in your empirical setup that isn't just about capacity, it's about some other problem. And all you have at your disposal is regularization, so you say, well, I'm just going to regularize more, and increasing lambda will improve things until validation performance looks stable. This is not going to work. You might get to a point where you improve validation performance on your validation set compared to some initial attempt, initial training, so things get better, and then the problem is you'd say, well, this is the best we can possibly get. We improved regularization and things improved, but they're not going to improve any more than this, so we're finished. This ignores the fact that the problem wasn't anything to do with capacity or overfitting versus underfitting. The problem was label noise, or the problem was leakage, or the problem was some other kind of statistical bias in the available data. So just changing the weights or the capacity of the model is not going to be, it's not going to really help you. Okay, so regularization, like basically everything else in machine learning, is not a silver bullet. So that's a scaffold. Let's talk to the lo-fi girl and the math lens. So we're going to define things a bit more now. We still have the same old definitions as before. We have training data. Now we're dealing with some kind of supervised learning. We have x's and y's. We have n of those data samples. We have our model, which is a function of x with parameters now w. Before this is theta, the same idea. The loss is some measure of difference between the truth, or the observed labels, y, and the predicted labels, f sub w of x. We have our penalty term. So our regularized objective, we've already defined it really, but just here it is a bit more, in a bit more detail. I mean, mostly I'm just labeling things. So this is the first term of the regularized objective is this first term, which is the data fit on training data, and then the second term is the regularization. So regularization is just a function of the weights, and given the weights, we can extract some measure of how wild they are, how crazy they are. Speaking informally again, and this is a bad thing we want to minimize. So we want to minimize both the error on the training data, and we want to minimize the wildness of our parameters w. And this gives us our overall regularized objective. Again, r hat of w using the hyperparameter lambda, which is shown here as a subscript. I mentioned a moment ago, lambda being a hyperparameter means we can choose it via cross-validation. Again, a topic we touched on earlier and we'll touch on again later. Now, we're at a point now where we're omega, which we define generally as just like a penalty term. Let's define it. So we have multiple choices of omega. Omega will give us different regularizers. And we're going to focus on just three of the most popular ones. In L2, omega is defined as the 2 norm of the weights. So you might remember this representation from earlier. This is just, well, we'll see it in a second, but this is sort of the quadratic distance. L1 is the 1 norm, or the Manhattan distance. We'll see that in a second also. And then the elastic net is a combination of both. It's flexible, so it's as you'll see in a second, it's an elastic combination of both, as the name suggests. Again, one more little peek into intuition. We'll have this high degree polynomial, and I want to show you an unregularized versus a regularized version. In blue, these blue dots here are our very small amount of training points. And the blue line you can see here in the background, kind of, is the true function. This is the reality that generated these points. Now, we have two approaches to training. We have an unregularized fit using MSE as our loss function, and without any other regularization, which would result in this orange dashed curve over here. And then we have a regularized one where we basically like squeeze the parameters a little bit so that the function doesn't fluctuate so wildly. I base this graph on graphs I've seen in other courses. The graphs I've seen on other courses are meant to show the same thing, which is if you fit something in an unregularized fashion, a function will fluctuate wildly, compared to regularization, where the fluctuation of the curve of the fit is much calmer, much smoother, much less in terms of drastic amplitude changes. In the other work I've seen before, it was entirely theoretical, and you see like the unregularized fit being absolutely crazy. And I didn't want to do that here just because like this is based on real data. This is kind of behind the scenes here, but this is a real regularized fit and an unregularized fit using functions I'll show you in a moment. But this is much more realistic to what you're more likely to see with real data than the crazy, absolutely cartoonish fluctuations in other courses. But the end result is the same. An unregularized fit, as you can see here, does fluctuate pretty wildly away from the truth, especially if you go to very small values, less than 0, or very big values, bigger than 1. This orange curve will give you predictions that are in the hundreds or the minus 100s, respectively, which is very different than what the true function of y equals 0 should give, right? So that wild fluctuation is a result of very big numbers. Actually, we can see that here. So this graph down here shows in the blue dots are the actual values of the coefficients for my function. I don't know what order this is. I think it's like the first one would be times x, the second one times x squared, the third one times x cubed, and so on all the way up until x to the power of 20. So these are all just the coefficients for our function. And you can see how wild these are. They go into the hundreds of thousands and to the minus hundreds of thousands in terms of their amplitude. And that wild fluctuation gives us this relatively wild fluctuation of the orange curve, whereas the regularized coefficients, this is ridge regularized. I haven't defined ridge yet by name, although we saw it a moment ago. You can see that the coefficients are much smaller. They go from like minus 5.5 to about, minus 0.5 to about 0.1. So the coefficients are a lot smaller, and then their difference over the range is also a lot smoother as well. This is all generated from real data, so this is what we'd expect from real regularization. Even though the data is synthetic, it's much more realistic than what you see in other courses. So just defining things, L2 regularization is called ridge regression. And for linear or logistic models, the L2 regularized objective is this. This is the regularized objective from before. On the left, the first term is our good old-fashioned training objective on training data. And on the right is lambda times omega, and omega is just the sum of the squares of the individual weights in my model, where like an individual weight is W sub j. Okay, so if W is very big, this gives me the squared value of the coefficient, of the weight. And I don't like big weights, so I want this to be as small as possible. So I prefer an empirical risk in which this term, which I've highlighted in blue, is as small as possible. So if you have huge weights, like the ones we saw on the left here, unregularized, you'll have a very high penalty. And if you have small weights, like you see over here, including negative weights, the square of them will be relatively small, and that's preferred in this regularized objective, which I'm trying to minimize. This will encourage solutions with kind of spread out moderate-sized weights, which we saw again on the last slide. And the main effect of ridge regularization is that weights will be shrunk. They'll be shrunk, or shrinked, I guess some would say. This is English probably allows for both of those terms. But as you can see, very few of these terms are actually zero or close to zero, like relatively, but they're kind of spread out. The idea of L2 is don't let weights get too big, but instead prefer smoother, less wiggly fits, like you can see here. Wiggly is on the left. L1 is called lasso. It's the same form as before. We still have the regularized function with omega, but now omega is just the one norm, which is just the, well, effectively the one norm, which is just the absolute values of these weights. Mm-hmm. So here again, the intuition of L1 regularization or lasso penalizes the sum of the absolute values. However, like, empirically, this will encourage sparsity. When you use lasso, many of the weights will be driven to actually be exactly zero. And this is just effective just squaring or taking the absolute value. When weights go to zero, then that feature that it's attached to effectively is ignored. In regression, where all we're doing is taking x and x squared and x cubed and so on, then it's just basically turning off some of those factors in the sum of the regression. But if we're dealing more generally with, I mean, this is maybe getting ahead of ourselves a little bit. These modules in the future are going to be about features. But if you have different weights on different features which mean totally different things, like representations of the data, things I've computed previously, computing a lasso and making the weights of those features go to zero effectively turns off those features, and it's a way of doing feature selection. I say these features which I've determined the weights can be zero are not important, and these other features in which I've allowed the weights to not be zero, those are relevant to me. We're effectively doing feature selection. This is a bit of a preview for something that we're going to see later in this course. L1 prefers solutions that use fewer features strongly rather than using a lot of them to a diminished amount. Here's a mnemonic I use, and I periodically have to remind myself of. Which one is lasso, which one is ridge, how are they defined? L1 is first order, so the 1 in L1 refers to the first order value of omega. So first order, you're not squaring anything, it's just the absolute value. L2, the 2 refers to the second order function because we're squaring the weights. So L1, first order, L2, second order. That should be super easy to remember. A little bit more tricky is, well, is L1 lasso, is L1 ridge? This is the mnemonic I came up with. I'm not sure if it's going to be helpful, but L1 comes before L2 alphabetically. If you were to sort these words, L1 would come before L2. And the word lasso comes before the word ridge. So that means L1 is lasso and L2 is ridge. Okay? Just because that's the order alphabetically of each, and they match up. So hopefully that helps a little bit. You might come up with your own mnemonic, but often students in classes like these need to come up with such hacks. So those are two forms of regression. There's one more I promised we'd mention, which is elastic net. This is a mix of L1 and L2. We're just going to combine both of those penalties. Maybe we like the fact that L2 diminishes weights. We like the fact that L1 can turn off weights and set the coefficients to zero. So all we do is combine them. We're still going to have an overall hyperparameter lambda, which refers to the overall strength of regularization. Now we have another hyperparameter alpha. Alpha can be anything between 0 and 1 inclusive. And we're just going to multiply the one norm loss, the L1 loss, or the lasso loss, which is on the left here, by alpha, and then we'll multiply the L2 loss, or the ridge loss, the 2 norm, by 1 minus alpha, so like the reciprocal, I guess, of alpha. If alpha is a 1, then we're dealing with pure L1, because it's 1 times the L1 loss plus 1 minus 1, which is 0. We ignore the L2 loss. And similarly, if alpha is 0, then it's pure L2. And you can imagine alpha just being basically a balance between L1 and L2. Okay, so that's all it is. We're combining both of these losses because we like aspects of both. We have a hyperparameter alpha we have to introduce to basically weight the extent to which we're leaning towards L1 or L2, and we're otherwise finished. Why do we do this? I mean, you always do things empirically. You'd always just try to run the experiment and see what happens. But the rule of thumb is L1 by itself can behave poorly when features are correlated with one another. Sometimes you have two features which go up and down or like opposite to each other. I guess if they're negatively correlated. And if you are just doing L1 on a case-by-case basis, this can result in somewhat arbitrary selection. So you might get certain features being turned off that you don't want turned off, and other features staying on that you wouldn't mind having being turned off with zero weights. And L2 doesn't really give you sparsity. So if you want to do something like feature selection and turn a very complicated model into a more simple model, again, because reducing capacity can help you generalize or be more flexible to other data in the future, which is the whole point of regularization from the first few slides. L2 will still not change the total number of features we have at our disposal. They'll just change how much, the extent to which those weights fluctuate. So we like both of these things. We want to combine them. ElasticNet gives us that combination. So it encourages some sparsity, but in a stable way. So examples. Let's do L1 versus L2 on a noisy classification task. We're going to have a synthetic binary classification data set with a small number of features that are informative and many features that are noisy that we could very happily ignore because they don't tell us anything about the signal, about the label we're trying to predict. And we're going to have two logistic regression models. We're going to do logistic regression. One of them will be regularized with L2. The other one will be regularized with L1. They'll both use the same regularization strength lambda. The only difference will be the function L1 or L2. So go to the slides, get the code. What's happening here is I'm using a lot of sklearn to basically make this classification task. I define the number of samples, the number of features, how many are informative, how many are redundant, any repetitions, the number of classes. It's 2 because we're doing binary classification. I set the random seed. This is something we generally do, again, to make sure that any stochastic process where random number generation comes into effect is repeatable, because we'd like to change this so that we can get a range of possible random numbers, but for the point of view of just repeating exactly the experiment, we set the random state. Then we do the train test split from sklearn. We do some standard pre-processing. There's a little bit behind the scenes here, but here is where we define the L2 classification pipeline. We're getting ahead of ourselves a little bit, but we use a standard scaler. We use a logistic regression model. The penalty is going to be L2. The capacity, the C is a C value. A lot of the rest of the stuff we haven't really talked about before. The maximum number of iterations we're going to use for training this logistic regression will be 1,000 and so on. As you can see, the main thing to see here is that all of the settings for L1 CLF and L2 CLFs are two classifiers. The only difference between these are that one takes the L2 penalty and the other one takes the L1 penalty. And then I fit both L2 and L1 to the available training data, and then I compute the performance of those fit logistic regression models on the validation data, which we obtained a moment ago from the train test split. And then I report on it. So super simple setup. One reason I'm kind of getting into this a little bit is that prior to this, when we're talking about regularization in the context of machine learning, we were using regression, so we can see curves that were fit to data because we were doing regression. Now we're doing a classification task, but the same kind of penalty can be applied to your empirical risk, to your overall objective function that you're trying to minimize. And this is handled behind the scenes now for you automatically using sklearn. So we see a little bit of, so this is empirical. Things kind of line up the way we'd hoped. L1 and L2 get very similar performance, so the validation accuracy in both cases is about 71%. So it's great. The main obvious difference is that L2 regularization results in 20 non-zero coefficients. but logistic regression with L1, or lasso regularization, resulted in only 8 features that survived regularization. All other features were set to 0 in terms of their weights with L1, which is kind of what we talked about theoretically a moment ago. So yeah, often in settings like this, especially in synthetic ones, L1 and L2 will perform similarly. Again, you never want to take anything for granted. You always want to do the experiment because you're scientists and you're smart, and you don't want to trust your intuition. So both L1 and L2 based regularization is doing a good job at classification. The main difference is the non-zero coefficients, and the difference is one we expected and we observed through experimentation. In this data set, the first 4 features were the ones that were actually informative, and this is something that we forced into making the classification task in the code a moment ago. The rest were just combinations of truly informative features or just random noise. So switching off some features was actually a good idea because many of the features were noisy, many of the features were redundant. The overall result was a model with fewer features that we'd actually use, which would mean, first of all, we're doing explainable AI. We're really ahead of ourselves now, but by choosing which features were informative, now we can say something about the data and the model and the important relationship between X and Y. We're explaining something about how the model works just by seeing which features L1 switched off, which weights it set to 0. So it's more interpretable, it's sparser, which might mean that it's more efficient to run, it's cheaper to run. You might save some money if you're doing this. I mean, at scale, if you're running millions of models, having a model that's less than half the size of another might take an order of magnitude less compute power and save you a lot in terms of your pure costs. Here's visualizing the patterns. There's nothing much here. I had to change a couple of these things. Like it worked in one operating system but not the other. But the fundamental aspect of this visualization should be the same. Here are just the weights in absolute terms between what we obtained at the end of training with L2 and L1 regularization. And you can just see a little bit of the difference. Some features, like this feature I'm highlighting over here right now, both L1 and L2 determined it to be relatively important and gave a high weight to this coefficient. But L1, these black squares over here, you can see a lot of these features are literally just set to 0, absolute 0. In other cases, L2 found that these parameters aren't that important and set their values of those weights close to 0, but not exactly 0 in most cases. But generally, the overall pattern is similar. When L1 sees a feature as being important, it'll give us a high value for its coefficient. Similarly for L2, and you can kind of see most of the time they agree with each other, with a couple, as I'm highlighting right now, in the middle here around the feature index 12.5, there's some ambiguity, there's some difference. So this is all as I mentioned a moment ago. You can try changing the C value. So again, take the code I'm providing you and try to break it and just try to get different behavior based on different settings. I'd recommend you try changing the C value. If you change it to be smaller, this will effectively be like stronger regularization. C value is essentially means a similar thing to overall capacity. So smaller capacity means stronger regularization and hopefully a better ability to generalize. You can take the code that just generated the classification problem and change the number of features or change the number of those that are actually informative. So look at this function, make classification, and then just change the setup a little bit and end up with a visualization of the type we see here to see if these trends continue. And this generally see if there's a balance between accuracy and sparsity in your own experiments. This is just for your own benefit, but I truly hope that some of you are leaning into learning things not just for the sake of marks. So how do we choose lambda? This is the regularization strength, which I mentioned before is something you can set by hand. Hopefully I did the quotes visually there, because normally we wouldn't necessarily just set it. We talked about this a moment ago. One approach is to have a grid of candidate values. 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 2, and so on. I mean, maybe you're not going to change things like, logarithmically this way. Maybe you'll have a grid of values you want to explore in some other way. You have a range of possible values. For every value of lambda, train the model, estimate the performance on using cross-validation, and record it. Again, go back to module 13 to recall how cross-validation works. And then you'll have a lot of different values for different settings for lambda. Pick the one that gives you the best validation performance. Maybe you want to see a trade-off between L1 and L2. You have some other aspect you want to observe in terms of the setting of lambda and their effects. And then when you're deploying it, when you actually do your experiment on your test data, your final test data, you'll use whatever single setting of lambda you've optimized through this cross-validation approach. Again, low values of lambda means you're not regularizing very strongly and you're relying more on the training data, and you risk overfitting. You don't like that. The whole point of doing regularization is to avoid overfitting. So setting lambda to be higher than just really extremely low can avoid overfitting. The problem is if you're too high in terms of lambda, then this really turns off your weights, which minimizes the capacity. And as we saw earlier with with regression, when you make a model it's too simple for the data you have, you risk underfitting. So basically, moving lambda back and forth can scale between the risks of overfitting and the risks of underfitting, respectively. Again, we care about responsible AI because we're likely to deploy AI in the future. So let's just think for a moment about regularization in practice and whether there's any ethical implications. And as you might expect, there are ethical implications. Occasionally, you can hide systematic bias rather than addressing it. Again, if you're just going to optimize lambda through some cross-validation or on some held-out validation data, and you get to some point where you've improved the overall performance, on your larger training set, and you stop there, this doesn't mean this is the best your model can do. Any kind of problems related to data leakage or demographic problems or other kinds of statistical bias would still persist even though you've used regularization. So regularization can give you a false sense of security. Relying on a single proxy feature that might represent a protected attribute could mean that you're doing classification but in a biased way. So all the regular problems still exist. There's a kind of a dial between interpretability and misuse. L1 can make models easier to explain by regularizing with L1 and automatically ending up setting some of the weights to 0, results in another set of weights whose features are not 0. This can be a form of explanation. It can say, well, the important features to my classification task or my regression task are these, and you can explain them qualitatively or in terms of domain expertise. But sparseness doesn't mean fair. Sparseness doesn't mean causal. We might talk about causal, like reasoning and causal machine learning later in this course. But again, just because something is interpretable, it doesn't mean it's fair, doesn't mean it's causal, and it also doesn't mean that you actually understand it. Interpretability, the problem is still between the keyboard and the chair in many cases. So robustness, regularization can improve robustness to random noise, but it won't necessarily protect against adversarial inputs or distributional shift. So if you deploy something and then the conditions on the ground change, regularization might help in terms of robustness, but it won't, again, be a silver bullet. I want to speak to the curious among you. Hopefully you all have a certain amount of curiosity. We're going to start seeing deep learning later in this course, and even though we spoke in terms of logistic regression and good old-fashioned regression in this module, the same concepts will keep on coming up, and we'll see it again when we talk about neural networks. So good old-fashioned L2 regularization applies in neural network training. Of course, the parameters in neural networks refer to the connections between artificial neurons and not just the coefficients on regression lines or curves, but the exact same term would apply. The same omega being L2 would apply. You might have heard of dropout. You're going to hear about it later. But dropout basically takes a neural network and kind of atrophies some of the connections. It zeroes out the activations on your model. This is a form of regularization in terms of neural networks. And it's very similar to L1 in the sense that we have a model with a big capacity, and we force it to have a smaller capacity by setting some of its parameters to 0. Again, L1 does the same thing. There's this concept of batch normalization and data augmentation. This will help stabilize training and improve generalization. So again, improving generalization is what we're trying to do, and batch normalization, data augmentation are other ways we're going to try to solve this problem. But even though often they're just described as such, we're just doing normalization, we're just augmenting our data set. Others view those terms as a form of implicit regularization. And then, transformers and large language models, those are highly parameterized. This risks being like really overly capacious models. So having strong regularization and careful tuning will be critical to make sure that those massive models are not overfitting to tiny, small, static data sets. Please perform the quick checks and make sure you're understanding these concepts. There's further reading I've linked to here on the elements of statistical learning. I don't think I link to the actual chapters here, but maybe more specifically, there's the original paper on L1 or lasso is here from 1996. There's a pretty good paper from 2019 on modern machine learning practice, the bias variance tradeoff, that discusses concepts related to regularization. And then there's this course from Andrew Ng at Stanford, which is a university towards the southwest of us, that talks about the same concepts. Go ahead and check out those slides as well. Here are your references. As usual, it's been a pleasure, and I'm looking forward to seeing you next time.